Okay, hello everyone. This is additional video just for your information, and this is I will talk more about exponential. Okay, as you may know from our course, we already learned that if we have this derivative, this will be same thing as the original equation, and I think this is uh, one of the important function, because the derivative is same as its function, right? Or if you would like to write in a more dy dx, it is same as y itself. Okay, this is why it's important. Okay, now if we are going to look back at before we find what is e, we are having some exponential functions such as 2 with the power of x, or 3 with the power of x, or maybe 8, maybe 9, right? And then you can draw the graph, right? And maybe before we draw the graph, let's see, we are imagine this these functions as populations. Okay, so p dt is for time, and let's say we are imagine this as populations. So this means the person or maybe creature. Okay, if you imagine this is a population of a creature, it's doubled every t, right? So at t equals 0, oh sorry, should be 1, and it's keep doubling every day. So imagine you have the creature here, okay, very cute creature, and then it's doubling. It's also doubling. Is t equal 1, and then keeps doubling. And you'll see that as t is increasing, it keeps doubling every time, right? So okay, let me. So the rate of change of the population this is our function here. So the rate of change will be divided by dt. Okay, and we can start to observe, okay, between day 3 to day 4. Okay, so if t is time for days. Okay, let's use our GeoGebra. If you had the apps, you can download the apps. Okay, so here it is, the 2 with the power of x. Okay, so here is the graph, or maybe let me put some tools here. Let me put a line between 3 and wait. Okay, go here, maybe here. Okay, so okay. 4 is here and 3 is there. Okay, and then let me just take screenshot. Okay, and let's put in our notes here. Okay, now we are looking at from t equal 3 to t equal 4, and we can imagine if we are going to use our rate of change definitions in limit, if you remember. Okay, so we will have this triangle here. This means the population here, and this will be the time. So this will be time and the populations, right? Okay, now if you see here, so the rate of growth or the rate of change between 3 and 4 is grow from 8 to 16. If you are looking at t equal 5, this will be doubling. So okay, if you look at this, so it's growing, right? It's doubling. Let me write here, doubling, and also doubling, right? And of course, probably at the beginning, before you learn about exponential and all the things in derivatives, probably you are thinking that, oh, probably if we are looking at this, maybe if we are trying to derive this will be resulting with the 2 with the power of t, right? Let me make a question marks. So probably it's quite tempting to be like this. Is it true, right? It's on right direction, but not quite correct. Okay, it is correct if only changes in delta t equal 1, right? If you are looking at here, it seems that should be correct, right? But remember, because we are evaluating the derivative or the limit at every point of this function here is to the power of x. So we need to also look at when we are changing our a or our b here. So maybe we are changing our a, it's going closer here. The triangle will be different, right? The triangle will be different. And then maybe going more closely with b, maybe going here, and it's also different triangle. And you will see that when you deal with the tangent line, it's all going to have different. So if you are changing the delta t, 2 with 3 with 4, the line will be also different, right? So how do we make deal of this? Okay, so okay, let me write the limit. Okay, or maybe not using limit, so just the rate of change. Well, it's actual limit, but I will write in terms of just rate of change in a small time. And we need to figure out what it is, okay? So we need to make our time is really, really, really small. So we need to find, is there a way we can make this in a logical sense, okay? So let me put in the same graph. Okay. Now taking this and look at this. And we can make this and of course we have this. So look here first, okay? We are still not using limit here, but just to make you think that when you are dealing with this, okay, and you are thinking, oh, maybe this is correct. Yeah, in some senses, it's probably correct, but it's not really that correct, okay? So if you are looking at in a small manner in t, we get the idea that actually we have this original functions, right? This original pt, right? And it's multiplied with some constant. Multiply with some constant here. And of course, you remember that if we are dealing with limit, we can make up this into some value, right? Okay. Oh, sorry. Should be 1. So constant. So in limit as dt approach 0, this will be a constant independent of t itself. That means when you are going to change the tangent, all tangent will have the same proportion. So when you are dealing with, like my example, dealing with t is very, very small, like maybe 0.00001, then the idea will be, how many zeros is this? 60. Okay. And then divide by 0.00001. This will be approximately 6931472. So every time you look at the graph, the slope will have this proportion. Okay. Okay, let me go. So earlier you are trying to look at, maybe I write, okay, so this will be, so it should be has a constant here. So the slope okay, and then we try with 3, and it also has some proportion, some constant that is proportions. And you can also try to check and you look at the pattern. Okay. Okay. So the sum, let's say sum B, and then we have sum B, D, and then a constant. And then by some extensive trial research, some mathematicians find out there is so the question is there a base where that constant is 1? And it's actually E. Should be 8 to 8. So when you have E, you try to some evaluation on some number that close to 0, very, very small. We'll get that this is actually getting closer to 1. Yeah, around that number. So in limit, this will be limit as dt, this will be equaling 1. So E is unique because it's proportional. E is unique because it's proportional constant is 1. So this is the uniqueness of E. So let's get back to our GeoGebra. Let's hide all this and maybe creating another one that is E. Okay, now we have this E. Okay, so this is E, and let me capture this, take a screenshot, and then back to our notes, and let's make some little conclusion here. Okay, look at slope. I think there's also students asking this question about the slope here. So let's look at x equal 1 here. So this is the point here. So this is, let me remind you, this the function is e to the x. Okay? And then let me draw the slope. Probably, let me make the thickness. Okay, maybe like that. Okay, maybe that is the slope at x equal 1. Okay, let me. All right. So this is slope. The slope is e. Okay. And the height also e, right? E. So is also e. The slope and then the slope at x equal 1 is also e. Okay, that's how it is, and why the e is unique and important. And also, you already learn about chain rule, so you have this idea here. If I derive this will be, first we write e 3x with that power, and then multiply with the chain rule, right? Because of the chain rule, we need to multiply with 3, so this will be 3 e 3x. So okay, this is chain rule. So the idea is, whenever you have e with some constant and then some variable, this equal to some constant e and then constant. Okay, and this is important in some application. We can also write, okay, as a conclusion, okay, from all these discussions, we can go back to this findings here. So the number 2 we can also write as e with the power of natural log of 2. So log, okay, logarithm, it has base, right? It has base, it has so if we are writing the for example, the exponent b with the power of x equals some a, we can write log b a is x. Okay, when b is e, we can write ln. So log e is ln, right? And one of the property of that log, when you have e, and you can write this, you can rewrite 2 with e with ln2. And this means that e with the power of, the question is just this, is equal to. Okay, so the idea is by powering e with ln2. Okay, and then if you are adding t, this is just adding t. So if we derive this, okay, derivative, okay, this will be proportions with the proportional constant 2. Okay, you can also think from these cases here. Okay, because you can write this 2 with the power of t with terms of e ln t. When we are dealing this, we derive this, and e is just becoming the e itself, the same component, but need to be multiply with its chain rule, it's ln2. And if we remember that this is our proportional constant. So proportional constant means there will be a constant, depends the constant depends on b, or base depends on base. Okay, and then this ln here, this ln2 here is actually our constant 0.693 blah blah blah. Okay, and when you have probability 3 with the power of t, and then ln3, okay, this will be equal with 1 point something, 1.0, what, 1.1 or 1.09, yeah, 1.09. Okay, so you can prove it using the one formula that you're familiar, like in logarithm, or trying some value here and then discover that e is actually this number. Okay, and then if you're later on looking at calculus, we'll always see that this will be always e with the power of x. And the other thing here, the change here, for example, this is just take e and then take the constant and then multiply with x, e with the power of cx. So that's why e becomes important, because it is foundation on every exponential phenomenon. So when you have e, so you can write this is e and 2x, or this is 2 with the power of x. So every time you have rate of change and you have an increasing rate, you will always get E in any formula that includes rate of change. That's how special E is. Okay. I hope that is enough for just additional video. This is just to help you more in getting in more details and more elaboration and in getting the number E. Okay.